Okay, now we come to the last section of this chapter, the convergence of line search method. Okay, um, after we run line search methods for many iterations, most probably we'll come to a situation where the gradient of the function, okay, at a certain point is zero. Okay, that means, okay, if I present this in the one dimension case, okay, I mean one variable s, this is the fs, okay, we come when we are converge, okay, come to this situation means that in this case we come to this point, we find this s, okay, this s, or we call it as s prime, which give us the minimizer of the function. We converge when we reach the minimizer. Okay, we reach the minimizer, we have converged. Okay, in two-dimensional cases, what I mean is a case with two variables, say s1 and s2. Okay, would we plot the contour? If this is the contour we have for the function, okay, then once we reach the minimizer, we come to this point. Okay, we come to this point. This is the minimizer. Okay, we have converged when we reach the point. Okay, so line search methods uh, converge when we reach the minimizer, but in some cases we converge also. I give you an example of a one dimension case. This is the fs, this is the s, wait, let me draw. Okay, we may converge, okay, when we converge, okay, we converge when we reach this point, minimizer. But in some cases we also converge, I mean we get the gradient as zero when we reach a saddle point here. Okay, the saddle point is a point where the gradient is also zero. So when we reach the saddle point here, okay, we will converge. For example, if you have fs equal to s cubed, okay, you can find the saddle point at s equal to 0. This is not a minimizer, but it's a saddle point. Okay, if you want to, okay, let me explain with the graph. This is a saddle point. Okay, drawing is not good. Okay, for fs is equal to s cubed, you see this point is a point where the 0 0, okay, s0 y0 is a point where the gradient is 0, but it's not a minimizer, right? So we will converge. Okay, we converge when we reach a minimizer or we reach a saddle point. Okay, so this is what I mentioned here. Okay, for the algorithms we have learned, okay, steeper descent methods is a globally convergent algorithms or methods. Okay, what I mean here is no matter where we start, our search, okay, you using the steepest descent methods, you will always converge to a saddle point or a minimizer. Okay, we will always converge to a saddle point or a minimizer. Okay, if we use the steeper descent method, okay, which is very good, but the issue is steeper descent method is always slow, okay, compared to the Newton methods or quasi-Newton method. Especially when the function is complicated, it becomes much more slower. For Newton method, okay, it is very fast. Okay, actually is the fastest among all the three. But the issue is it may not converge if the Hessian is not positive definite, or you start the search from some point which is very far from the minimizer. Okay, so here I compare the rate of convergence of three methods. The steeper descent, okay, as I mentioned just now, the convergence is slow, or sometimes we call it as a linear convergence. The convergence rate is linear. Okay, this one I will explain again later. And it has a zigzag behavior. Zigzag behavior means that, okay, if I present this in the in the contour, if you start from here, okay, it won't. It's very hard for you to observe something like this in the uh, simple distance method. No, most probably you will have something like this. For simple distance method, you start from here. Let's say you go here, go here, 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 here. Okay, zigzag. Okay, you can see this zigzag behavior for simple distance method. And for the Newton method, okay, the convergence rate is very fast, quadratic convergence. We call it quadratic convergence. Okay, um, if we don't consider the line search, okay, I means we have the alpha. I mean the step length is equal to 1 is always fulfill our requirement. It can be very fast. Okay, but the issue is it does not work when the Hessian is not positive definite. Okay, when the Hessian is not positive definite, okay, it won't work unless we want to modify the Hessian. Okay, there are some ways to modify the Hessian, but we wouldn't cover here. And the third one, so-called the quasi-Newton method. Okay, the convergence rate is so-called the superlinear. Superlinear is a convergence rate which is faster compared to linear. Okay, but slower compared to the quadratic. Okay, it's between the quadratic and linear. Okay, and also the quasi-Newton methods require the step length equal to 1. Okay, when it reach the solution, it reaches the solution, you can always assume that alpha equal to 1 is something workable. Okay, what I mean by linear or quadratic or superlinear convergence is something defined here, but don't worry, I will just explain it with this example. Okay, so for so-called the linear convergence, you see, when we start the first iteration, okay, if the value we get, okay, is 0.8, okay, okay, then after the one more iteration, the second iteration, it becomes 0.64, which is equal to 0.8 times 0.8. Okay, you get 0.64. This is so-called the uh, linear convergence. Okay, maybe I explain some more example. So when you have the second iteration with 0.64, okay, the third iteration you get 0.64 times 0.8, you get this one. And then for this one, you times 0.8 some more, you get this one. Times 0.8 some more, you get this one. So this is the so-called the linear convergence. Okay, they converge in a fixed by dividing the same number again and again. Okay, this is so-called the linear convergence. For quadratic convergence, okay, if the first term you get is 0.64, okay, and then you see 0.64 times 0.64, you get this number, or you can just say 0.64 square, you get this, and with this you square, you get this number. Okay, you see it converge much faster compared to the linear, right? In 1 to 3 iterations, you already reach 0.167 already. Okay, so it's about here already, right? So linear convergence is slower compared to the quadratic. So this is just a square of it. This one square, you get this number. This one square, you get this number. Okay, so this is a quadratic convergence. Superlinear is always between about between these two. Okay, so yeah, that's all for this lecture. Okay, today we are going to discuss the line search method. Okay, so there are 3 parts in the lesson. Firstly, we'll look at what is the line search method. Okay, we continue to study the line search method, including the direction and the step length. Second, we want to learn about the condition of decreases. Okay, it means when we find the direction and step length already, we can proceed to the next step. Okay, next point. Okay, but is it an acceptable point? Okay, does it fulfill the condition of decreases, I mean whether the decrement of the cost function is enough or not. Okay, this is what we are going to study here. And then the last one is the one is a conversion rate. Okay, so let's start with the line search method. Okay, we start with the revision first. So the line search method is a iterative process. Okay, what I mean here is for a function given to us, for a cost function given to us, okay, we will always start at a certain point. Okay, for example, we start here. Okay, let's say we start here. Okay, this initial point we start, and then okay, we we will always from this point look for a direction, okay, and also a step length, okay, to go to the second point, and at this second point we do the same thing. We assume that this is the initial point. We look for the second point, or actually it's the third point in this sequence. Okay, by fixing the direction or and step length, we go to the third point, and then we continue the process until okay we reach the local or global minimizer. Okay, we will continue the process until continue the process of looking for the direction and step length. Okay, once we know these two, we can go to the next point, continue doing it until the end. Okay, so if we write this concept in equation form, this is the one. Okay, we always start at certain point. Sk is the point that you can say we start at. Okay, but of course when you start at, if this is really the first point, we can assume the k is 0. Okay, so the starting point, and at this starting point, okay, we first look for a direction we want to go, pk, the direction at point k. Okay, sk is the position at iteration k. Okay, and the pk is the direction we want to go at this iteration k. Okay, once we know these two, we look for a step length. Okay, how far we want to go. The direction is given to us already, we found already. Okay, and with this direction, how far we want to go. Okay, so the step length at iteration k we also need to find. So once we find these two, okay, this one is given to us, we know already, then we can find where will we be at the next iteration at k plus 1 for the next iteration. So this is what we are going to do, okay, in line search method. So yeah, this is what I explained just now. Okay, we determine the we know sk, we find the pk, the direction. Okay, and then we find the step length, we move to the next point. Okay, next point, and once we reach the next point, of course we repeat, continue until we reach the local minimizer. Okay, this is just an analogy of this process. For example, we are standing at this point. Okay, we are standing at this point. Okay, we are looking for a minimizer. Actually, we are looking for a valley. Okay, the deepest valley maybe. Okay, deepest valley in this area. Okay, so we are here. Okay, where we want to go. Okay, surely you will say, okay, if you are looking for the minimizer or the valley, this is the point that we want to go, right? We want to go to here. Okay, so what you do, you just directly go to here, is it? Okay, this is what we can do if we totally understand about the whole area. Okay, the whole area we know. But the issue is when we are going to do a line search method, when we are searching for a minimizer, okay, what we only know is we are here. But where is the minimizer? We do not know. It's just like our eyes are covered. Our eyes are covered. We just know that we are standing at a certain point, but we do not know where we can go. We don't even know where is the the direction of the localizer. So what you want to do here, you are going to move, right? You are going to move, but you do not know where's the best direction. So maybe you want to move to here. Okay, you want to move to here, you can move to here, but surely you won't move this direction. Okay, I mean you may move to this or this direction, but not this one. Why? Because when you are standing here, you know, okay, this direction, okay, this direction give you a lot decrement on your gradient. Okay, you can feel with your feet. Okay, when you start standing here, you can feel your feet. Okay, this is the direction that give you some decrement on your altitude, right? This direction also give you a bit decrement on your altitude. This one maybe not, but it's a flat area. I mean, going to a, I mean, if you go this direction, okay, you find that it's you are like moving on a flat, I mean, surface. So it's not a good idea, but still acceptable. But surely you wouldn't go this way, because you can feel going this way you are moving upwards. So you are going to go to a higher altitude area, right? So this is not what you want. But all these three are some possible solution for you to find the valley or the deepest valley. So what I mean here is we have actually more than three directions. As long as the direction, okay, doesn't lead us to a higher altitude like this, okay. Beside these three, maybe or this direction are all good directions to move. Okay, if you want to go to a valley, right? So these are the choice or direction you can have if you are here, okay, and you want to go to the valley. But for the line search method, okay, actually we are doing something similar. We want to choose a direction, okay, and there are three different directions we can choose. First, okay, three common one. I mean, first is what we so-called the steepest descent, okay, and the Newton direction and the quasi-Newton direction. Okay, so the steepest descent method that provide the steepest descent direction is this one. This direction. This is just a negative of the gradient of the point you are at. Okay, I repeat, this one I think I mentioned already last time. This one is actually means the gradient, okay, or the gradient, negative of the gradient of the point at xk. At the point xk, the gradient of that point. Okay, okay, you find the gradient of that point and the negative of it, okay, give you the steepest descent. Okay, the steepest okay, given by the gradient. So you just follow the one, okay, and this direction, okay, will lead you to a area which is lower altitude or lower, okay, in terms of the cost function. Okay, so the other one is a Newton method. Okay, the Newton method, okay, not only rely on the gradient, this one, okay, but it also multiply with the Hessian at that point. This one actually means this is equal to negative of the Hessian, okay, of inverse of the Hessian. I mean inverse of the Hessian of the point xk, okay, this one, product with the gradient of fsk. Okay, this is k. Okay, so this is the, okay, this is the Newton method. Okay, as we know, the Newton method has one disadvantage. What's the disadvantage of Newton method? You need to compute the Hessian. Not only you need to compute the Hessian has to be positive definite. has to be always positive definite. Okay, if this is not a positive definite, the consequence is you may move to a higher altitude, or you may move to position, a point which has higher uh, cost function value. Okay, so this is the problem of Newton method. Even though Newton method is fast, but you have this problem. Okay, the the improvement from Newton method is so-called the quasi-Newton method. The quasi-Newton method is something similar, but we just replace, okay, replace the Hessian, okay, of that point with the BK, inverse of BK. What is this? This is the uh, also actually is also a Hessian, but not the Hessian of that point, but from this point, okay, from the Hessian of this point, we find a compatible Hessian. We find a compatible Hessian B, okay, which is positive definite, but can help us to move to a better position. Okay, so this is the quasi-Newton method. The only difference is whether they use the real Hessian or the improved Hessian. Okay, the difference between steeple descent method and Newton method is whether you use the gradient only or you use the information from the Hessian, which is more effective if and only if the Hessian is always positive definite. Okay, maybe some of you will ask a question. Okay, why we want to uh, consider the Newton method? Okay, since this is very straightforward, right? If we use a steeple descent, okay, we follow the direction which has give us the steeple descent. We always will reach the valley, okay, very fast, right? You see, this is steeple descent direction, right? Okay, we just go follow this way, okay, and then we can go directly to the valley already. Why we want to go other direction, okay, which is not giving a steeple descent? Maybe look at this photo. Okay, maybe look at this one. You see, this um, okay, this one is what we see when we zoom out a lot from this point. Okay, when we zoom out a lot from this point, okay, we can see, okay, this is the direction, this is the steeple direction, we follow this way. Okay, but in fact when we zoom in, okay, when you zoom in to this part, maybe this is what we see. Okay, maybe this is what we see. Okay, let's say the point that we are standing at is this point. Okay, we can see the steepest direction, okay, or the valley, the direction of the valley, maybe it's this area, this direction. Okay, this is the valley, we should move to here. But when we are at this point, okay, we compute the steepest descent. You see, the steepest descent is not this direction, but this one, right? This one, okay, because we are standing at the point which is we are standing at the um, mountain area which is not flat at all. Okay, not all flat. So we will follow this direction, which is our steepest descent at this point. And then once we reach here, maybe we follow this one. Okay, so you see, we are not always follow the direction to the valley. Okay, if you use the steepest descent. So the example I showed you just now, this one, okay, this is the contour of a very simple function, which you can see the uh, minimizer is just, okay, like follow this path, you can reach easily. But if we are using, I mean, if we are considering some function which is more complicated, for example this one, let me copy. Okay, if you consider this one, you see, this is a contour, which is a bit more complicated. If you stand at some point, okay, here let's say, you can see, or this point, okay, you can see, we will, okay, the following contour, the speed direction maybe is here, but if you are here, okay, for example, okay, you may lead to other direction, okay, or you are here, okay, you lead to other direction which is not moving towards the minimizer directly. Okay, now just now we have talked about the search direction B, okay, with either Stephenson or Newton or Newton method, we will find a direction to move, okay, no matter which one we use, okay. After we find the direction, the next thing is we want to find how far we want to move, okay, the step length alpha. So the step length alpha is how far we want to move. Let's say we are standing here just now, okay, we already determined, okay, this is the direction we want to move. We can choose to move a bit only, a bit or a bit fast or further from the point we have, and then a bit more further, okay, or we can move very far. Okay, what's the difference? The difference is if we move the distance is too short, okay, we will need to take a lot of steps to reach the minimizer. Okay, if we move faster, of course it is faster. Further. Okay, of course it is faster, but if we move too far away from the point, you see, this is what will happen. We will miss the valley. In fact, we may go up to another point, which is higher. Okay, we don't move to the valley. Not only not reaching the valley, but we miss it until we go to a higher position where we need to move back again. Okay, so this is a issue. So this is why we want to determine what is the step length. Okay, just now we have already discussed the direction in the line search method. Now we continue to discuss the step length. Okay, so let's say assume we are here right now. Okay, we want to move to the valley, okay, or the local minimizer. Okay, it's an analogy of the local minimizer in your cost function. Okay, so let's say we already determined, not only we are here, we also know we want to move to this direction. Of course, the best thing is we can find, okay, the valley in one step. What it means is we can choose a step length. Okay, with this direction, we choose a step length which can lead us to the lowest part, okay, of the valley in one step. That means that also means we take one step only to reach the local minimizer. Okay, this is something we want to get, but it is not easy. Okay, if what I mean is even though it is possible, okay, sometimes it's not possible, but even though it is possible, it will be very costly to find this step length. Okay, so instead of finding this step length which can lead us to the lowest part, we don't do this. Okay, in what it means instead of finding this exact line search, okay, the one that lead us to the lowest part of the valley, we do in exact line search. That means we find some alpha, some step length, which can bring us some adequate reduction in the cost function. Okay, but the cost is minimal. As long as the cost is minimal and we have some reduction in the cost function, we can choose that alpha already. We don't need to reach the valley in one step. Means, okay, we don't want this. Instead, we prefer to have smaller step. We move slowly, okay, to the valley. Why? Because this one, even though we have more steps, actually the cost of finding each step is smaller compared to the one that finding one shot to here. So how to do this? Okay, typically the typical way is instead of finding that alpha, we have a sequence of alpha. Okay, we have a sequence of alpha. We just try out one by one until we find the first one, which we can accept. The first alpha that we can accept. Then we choose the alpha. We choose the alpha as our current step length, and we take the move. And then we go to the new step, new point, and then we do it again. Find the P direction, and then we find a acceptable alpha. Acceptable alpha from a sequence that we can accept. Then we take the alpha again. Just repeat. Okay. Let me continue to the expression with a new one. Okay, new page. 1 minute. Okay. Okay, you see, let's start the discussion from here. Okay, you see, if we are here, okay, we take a move when we can determine our direction and we know the step length. Okay, we move to a new step, new point. Okay, we move to a new point. Okay, or in general, we move to a new point. Okay, when at the current point, we can find the step length. The direction. Okay, at that point, and we can find the step length at that point. So with this information, we move to a new point. Okay, so at this new point, the cost function that we have can be written as this one, right? Seems like the cost function, is a function of the point. Yes, it is true. The cost function is a function of the point we have. This point have different cost function value compared to this point. This point has different cost function value compared to this point, and so on, right? The position is the variable we have in the cost function. Okay, but you see, when let's say we are at a certain point here. Okay, we are at a certain point here. Let's say, okay, this point, this point is already fixed. We already know we are here already. Then, okay, if we are at this point already, this one, okay, the sk, okay, or s1 here, s1 or sk here, is a constant, right? Is a constant. And when we are at this point, with certain methods like the steeple descent or Newton or quasi-Newton, we can find the direction. Okay, this point can help us to determine which direction we can go. So if sk is a constant, pk is also a constant. Okay, it's also a constant. Then the only variable in the function is the step length alpha. So we can rewrite this function in the other form where, okay, we call this function as phi, not f anymore, but phi, because this is another function where take the alpha, okay, take the alpha as the variable. What it means is when we know everything, okay, about the point, okay, I mean we know the point, when we know the point we are standing at, the alpha is the only variable that we need to determine, okay, to find the value of the function. Okay, so this this function 5, okay, actually is compatible, or not compatible, I mean it's equivalent to the sk plus alpha k pk. It's actually they are equal, but just we consider the alpha as the variable now. So when the alpha is a variable, when we are talking about this function phi, let's look at here. Let's look at here. Okay, let's say we are here. Okay, we determined already. We have determined this is the direction we have to go. Okay, this is the direction we go. Let's say, so you see, if I am here, I put in this s1, okay, s1 into the function, okay, into a function, okay, we find, okay, I plot the graph. Let me plot the graph. The phi, okay, is a function that the alpha is the variable, okay, and phi actually is actually the value of the cost function. So we know this one. Maybe for example, this is this point. I mean, when s equal to s1, okay, you put in s equal to s1 here, you get this value here. This is the value, let's say, okay. And when we take a small step, small one. So we take a small step, okay, to this point. Let's say this point to this point, the step we take, the alpha we take, the step length we take is equal to 0.1. Let's say small one, 0.1. Alpha is small value. Alpha equal to 0.1. You see, definitely, since we are taking the stabilization or Newton, we are going to down. Okay, we are going down. We are going to a lower value. So maybe this is what we get. Okay, we are going to a lower point. Okay, plug in this point to here. Okay, you get a smaller cost function. This point. Okay, so if we increase the alpha a bit to alpha equal to 0.2, you see we are closer to the local measure, so the value of f or the 5 should be lower, right? You can continue to do so. You can choose the other cost function. Okay, you can see when the the alpha increase. Okay, for this particular example, you can find your curve is like this until when alpha is a value like this. This is alpha, and let's say this is alpha n. Okay, you just reach a minimizer here. So when you increase the alpha to alpha n plus 1, okay, alpha n plus 1, which is larger, you will see the cost function increase because it's further from the local measure already. You see it's increase, and increase. Okay, so this will be the curve. This is the curve, okay, of the 5 versus the alpha, or this is a curve, okay, showing you how the change of the cost function when we change the alpha. Okay, this one actually is the cost function. Okay, alpha is the only variable in this cost function, so when it's further, when it's closer to the cost function, it's getting smaller. The cost function becomes smaller. When it moves further from the point, the cost function becomes higher. Okay, this is I show you with the example. But what if you have some other curve? This one is very simple. This one is very simple contour. When you have a function with contour like this, let me copy. When your curve with or maybe okay, here. When you have a function like this, okay, a function with contour like this. Let's say you are standing here, okay, here, and you move, okay, towards this direction. Okay, you move towards the direction, you see. Okay, the contour, sorry, the graph, okay, can be something more complicated compared to this one. Okay, okay, compared to this one. Oh, okay, compared to this one will be a bit more complicated. The graph you can get can be something like this. You see, you are at this point. Let's say this is the starting point of your cost function here. Okay, and then you move a bit. You see, you are closer. Okay, you look refer to the contour. You are closer to a minimizer, and then until here, okay, you reach a minimizer. Okay, along this line, okay, not this one. I mean, along this line, there's a minimizer here, and then it increase again. It increase again from here. Okay, and then reach another one here. So you can get a contour like this. Okay, sorry, you can get a graph like this, where this is 5, this is alpha. Okay, remember this, what I always mean here is we are not talking about a graph, okay, of one dimension, but we are talking about when we have a direction already. Okay, we take this direction, we cut here. Let's say you can immediately cut here. We are talking about how the contour change. Okay, along this line, you get this one. So now the question is, we are already here. Okay, what means here, this one. Okay, yeah, this is how you get the graph, something like that. Okay, we are here. Okay, at this point. Now, what is the alpha? What's the step length we want to choose to reach a local measure? Again, we cannot choose this value. This is the alpha, which is the best one, or this one. We cannot, because we do know what is the value of this. We do know where is the local measure, right? We are covered. Our eyes are covered. Okay, we cannot see. So how to choose? So we may try different step length. This one or this one. We check what is the reduction of cost function, and then we will determine from there. Okay, this is what we want to discuss in the next video. Okay, what I say in the last video is, when we already know where we are, the SK, the current position, and we from here, of course, we can find the direction we want to go, BK. If you have these two information, okay, let's say we are here, this is our SK, and we know this is the direction we want to go. Okay, so the next thing is alpha. What is the step length we want to go? Okay, we want to take. So let's say this is the direction we go. Okay, you see, when we determine when we want to choose an alpha, okay, the alpha we choose start from here. Alpha, we choose this level. Okay, this, I mean, at this point, the alpha is equal to 0, and we take a larger alpha equal to 0.1, and so on. Okay, you see, we can plot a graph. You can just imagine we take a knife to cut this. Okay, this is a minimizer, right? We cut this. Okay, and we cut this, and then we view from this direction. Okay, what happened to this contour is actually a graph like this. Okay, start from alpha equal to 0. This is alpha. Okay, this alpha when alpha equal to 0. Okay, the contour, the height of the contour, which is also the cost function f, is here. Let's say it's here. Okay, when the alpha increase a bit, okay, we take a small alpha, move a bit, alpha equal to 0.1. Okay, the cost function you see is reduced. Okay, because it's approaching the, look at the control line. You know it's getting smaller, lower, right? So it'll be here. Okay, so you plot the graph. Alpha equal to 0.2. Okay, here is lower some more. Okay, if you consider the whole line here, maybe you get a curve like this. This part, the lowest part, okay, refer to the part where the alpha is this value. Let's say this is alpha n. Okay, so alpha n, okay, you reach the local minimizer. Okay, and this is what happened. Okay, if we choose this direction, start at this point. Okay, but if let's say we start at this point, okay, and this is the direction we choose, the red one, okay, you get this line. Same thing, you cut. Okay, you take a knife and cut here. You will see, you observe the graph, okay, along this line is something like this. It go down and go up again and go down, okay, and go up from here. Okay, so this could be the curve you see if you cut along this line. Okay, and we call this as a function 5, which actually is also the f, but here we consider the x position and p direction as constant. The alpha is the only variable. Okay, now the question here is, okay, after we know the sk and pk, okay, the next thing is to choose is the alpha. Does it mean that we can choose any alpha? Okay, we can choose any value of alpha step length as long as this alpha, this step length, bring us to a low point. Means you take this step, small step, okay, right? You go to low point. You take this alpha, small step, it goes to a low point as well. You don't want to take this one because it may lead you to a too higher point, right? So is it means that any alpha along this line until here, okay, is everything acceptable? Is acceptable? Actually not. Okay. What I mean here is if the step length, this is the step length chosen as of sk lead you to the sk plus 1, as long as the fsk plus 1, okay, as long as the fsk plus 1 is less than the fsk, this alpha can be used. Is it? No, actually not, because firstly there are two reasons actually. First, if you choose small steps, okay, you may need a lot of small steps in order to reach the local minimizer, and this is very costly because for every step you need to compute the pk direction again. Okay, the first reason. Okay, and the second reason, which is more important, is okay, for some cases, for some functions, if you take small steps, you may not able to reach the local minimizer. For example, this one, when you have a small steps, when k increase, the step increase, you can see the decrement of cost function becomes smaller and smaller. Okay, the first, second, third, fourth, fifth, okay, and then the sixth, maybe you come to here, 7, 8, 9, and then you can see when k increase, you are just swinging, okay, between 2 points, just like swinging beyond 2 points, and you will never reach the local minimizer here. So we don't want something, okay, some alpha, just bring a little bit decrement on cost function only. Okay, our major condition, okay, suggests that, okay, we must have not only decrement in cost function, but we must have sufficient decrement on cost function. Okay, when we take a step, when we choose a alpha. Okay, here what it means is the reduction of cost function, okay, the cost function reduction should be proportional to both the step length chosen, and also the directional derivative. Okay, the directional derivative actually is just a gradient. Okay, transpose the gradient product with the step length. Sorry, the direction. Okay, transpose the gradient and the direction. Actually, this one actually you can just imagine that this is the square of the direction. Okay, just like it's just about like the p square. Okay, but of course we cannot write p square here because this is we are dealing with vector, not a real number. But it's the effect is just like a real number. Sorry, the p square in a real number. Okay, so here what I mean here is the decrement, okay, should be proportional to the alpha and also this one. Okay, that means this one alone, the reduction of cost function when we reach a new step, okay, which is less than, okay, the cost function is less than the current cost function, is not enough. We must have additional term here. Okay, not only less than this one, but also have to less than this one plus this. This is the step length. Okay, when the step length is larger, this one should be smaller. Okay, you can see because this one is less than this one, right? This one plus this one. So when the alpha is larger, this one must be smaller. This is the directional derivative. Okay, when this one is larger also, this one must be smaller. But not only that, we have a constant C1 to control how large is this term is. Okay, how large is this term is. C1 is the constant which is not more than 1 but also not less than 0, positive. Okay, normally the C1 is a small value, for example 10 to the power of negative 4. Okay, to control the reduction is something sufficient but not too small. Okay, which cannot be achieved. Okay, so look at here. Look at this one. This one requires, okay, I repeat, this one is something, okay, less than FK plus C1 alpha okay, I take a shorthand, I write this one only. Okay, now you see this is the term, okay, the one we want to make it less than, right? So this is a constant, this one is a constant. Okay, this one is constant. Why? This is a cost function when we know where we are. Okay, we know where we are already, so this is a constant, right? You always get a fixed value, okay, with this point. Okay, this is a constant as well. This is a constant as well if we know the position, we know, okay, the gradient of that point, also the direction we choose is a constant also, right? So this is a constant, this one is a constant. The only variable we have here is the alpha, or we can rewrite this one. Okay, we can rewrite this one in the form of, if I call this as k, these two, combine these two as m. This is in the form of k plus alpha m, right? When you see this, you know actually this is a linear equation. Okay, this is a linear equation, just like y equal to k plus alpha m, where m is the gradient, k is the intersection, and then the alpha is the y. Sorry, it's the s. Okay, it's the s. Okay, the variable. So this is actually what we want here. What the reduction we want here is actually following this one, this linear equation. Okay, now imagine that this is the curve we have, the curve of 5, okay, versus the alpha we have. I mean this one. Okay, this is the curve we have. Okay, that showing how the reduction of cost function versus the alpha we choose. Okay, now if, okay, we are at this point at k right now, this is our cost function, okay, with the without the unusual condition, okay, we can choose any alpha, we can choose any alpha we have here, because you see, if I draw a line here, okay, a straight line here, you see all the alpha we choose will get 5, okay, which is lower than this line. Okay, that means no matter which alpha I choose, okay, I will get a lower point, even though this one, which is lower compared to the f we have right here. This is a f at the cost function at the current point. This is the cost function, okay, which is a bit lower. This is a point where the cost function is a bit lower compared to this one. We can choose this one as well, okay, if we do not consider the unusual condition. But if we consider unusual condition, we know the cost function at the new point should be less than or equal to not only the cost function at current point, but we need it to be lower than some constant that some value we have here, okay. And this one, the whole thing here, is a linear equation. It's a linear equation. That means we have this one, okay. This linear equation, okay, is the line that showing us if we take a larger alpha, if we take a larger alpha, okay, we move further, alpha is larger, then we should get a lower reduction, okay. I mean, should get larger reduction on cost function, okay. When alpha increase, the reduction should be larger. Therefore, you see, because all this part, okay, from here to here, okay, you have the cost function, okay, lower than this line. These are the part, or these are the alpha that we can accept. When we move to here, when we choose alpha here, okay, let's say this is alpha k, let's say, don't use k, okay, maybe let's say 10, okay, 10, just number 10, okay. When you choose alpha 10, the reduction of cost function is this value. The cost function is this value, not the reduction. The cost function is this value, but this value is higher than the linear equation that we have here, this one. So this is the alpha that we cannot choose. This is the step line that we can choose, okay. When we move furthermore, okay, to here, until here, you see, we still have the same condition. The cost function that we get is still larger than the required condition, this line, okay. So this alpha, let's say we call it alpha 20, this 20, alpha 20 is still not acceptable. But when the alpha increase until it cross this line here, okay, it's acceptable again. It's acceptable again because this alpha will bring us a lower cost function compared to this line, the dotted line, okay, which is the linear equation, this one. Okay, so this is what the unusual condition okay wants. It has not only some decrement on cost function, but it has decrement on cost function more than the cost function of current point plus an additional terms, which is proportional to the alpha and also the additional derivative. Okay, following what we have discussed just now, unusual conditions allow us to take any alpha, any step length, as long as the step length fulfill, okay, the requirement that the cost function is less than, the cost function we get is less than this linear equation, okay. But does it mean that we can choose small steps? For example, we are here, we choose a very small alpha, very small one. Okay, and then we go to here, and then we choose another small alpha, we go to another point, and so on. Is it what we mean here? um, Not really, because even though unusual conditions allow us to do so, but as I mentioned earlier, we do not prefer small steps here, right? We do not prefer small steps. If the step is too small, okay, not only we have high cost on computing the direction, but also it's possible that we cannot reach the locking measure. So the curvature conditions, okay, is a condition that prevent us to take small steps. What it means here is the gradient, okay, the gradient of the new point, okay, when it product with the direction, should be less than the gradient of the current point product with the direction, and also a constant C2. C2 should be a value which is close to 1, okay, but not more than 1, okay, should a bit less than 1, okay, to prevent we take small steps. Because you see, this one actually is a gradient of the function, right? It's a gradient of the function, so it prevent we take small steps to reach a gradient which is a bit smaller than uh, the function only. Sorry, a bit larger than function only. Okay, so you see, with this one, if we are here with this curvature condition, if we are here, we cannot move to this area. Okay, sorry, we cannot choose the alpha which is in this area. Why? Because in this area, the gradient, okay, is smaller than this point. So when you move forwards, I mean, take a larger alpha, the gradient will increase until this point, okay, I mean this point here, sorry, this point here, which is larger than this one. Then, okay, this point onwards, we have all this point with gradient which is larger than this point. Then we can choose, okay. So these are the points where all the these are the area where all the gradients here are larger than this point. So this area, this one or this area, okay, are acceptable by the curvature condition, okay. And here you see, once you reach here, the gradient of this point and this point same have the same gradient. When you move forward a bit, okay, I mean you choose larger alpha, the gradient decrease again, which become less than alpha, okay. When less than alpha, okay, you cannot choose anymore until this point. When you reach this point, this point, the gradient is equal to the gradient of this point, okay. And then if you move forward, I mean the alpha getting larger, the gradient become larger, and then this is the area that you can accept, okay, accept the alpha. So this is so called the curvature condition. Okay, unusual condition prevents small reduction in cost function, and curvature condition prevents small steps. So we can always combine these two to form a more complete requirements on choosing how to choose alpha. So the combination of these two, we call it as a Wolff condition. Okay, Wolff condition, again, just a condition like this. Okay, this part is the unusual condition, and this part is the curvature condition. So we just combine these two, where the C1 and C2 should be in this form, because C2 is always a small number, right? And C2 should be a larger number. Okay, so we call this as a Wolff condition. And when you combine these two, okay, you see this line is the one that we have for the unusual condition. This dotted line, or this are the one given by the curvature condition. So we must fulfill both. That means we can only choose this area where the curvature condition and the unusual condition both are fulfilled. The other one is so-called the Goldstein condition. Okay, actually this is something quite similar to the Wolff condition. Okay, So this is just another set of requirements which is very similar. Okay, just now we said that we have a unusual condition, also the curvature condition. Okay, so we need a combination of both. Okay, we need a combination of both unusual and curvature condition to find a suitable step length. For example, here we cannot use this area because not compatible to the unusual condition. Here we doing this one because it's not fulfill the curvature condition. Okay, so this is only acceptable area or this here. Okay, so you see, uh, instead of using both, actually we also can use only one only. Imagine if let's say we can find a condition, step length which is large enough but still fulfill the unusual condition. For example, we choose a alpha here, okay, which fulfill the curvature the unusual condition, okay, which fulfill the unusual condition. You see, is lower than this line. This part is lower than this line. Fulfill the unusual condition. Then we choose it already, as long as it is not too small. Okay, how to do this? Actually, the method is we use another algorithm called so-called the backtracking line search. Okay, it's simple like this. Let's start with alpha, okay, which is large enough. For example, we say alpha equal to 1. Okay, we just try with this backtracking line search method. We just try if this is the alpha. Okay, let's say this is alpha. Okay, we just test the alpha. Is it fulfill the unusual condition? We test on the unusual condition only. If fulfill the unusual condition, this is the alpha we choose. Okay, if we get the alpha here fulfill the unusual condition as well, we choose this alpha. Okay, but if when we have the alpha at here, the alpha we choose is here. Okay, alpha we choose is here. This is the cost function we get, and this is higher than this value. So the alpha equal to 1 does not fulfill the unusual condition, not fulfill. Then what we do? We reduce the alpha. We reduce the alpha to become a smaller value, okay, which is given by alpha product rho multiplied with rho. The rho is the value which is smaller than 1 but not less but bigger than 0. Okay, we reduce the alpha by this ratio. We get a new alpha. Let's say alpha, this is alpha 0, this is alpha 1. We get the alpha 1. Okay, we multiply with this ratio. For example, let's say 0.9. We get this one. Okay, we get this one. Let's say this is alpha 1. Okay, we get this one. Oh, now alpha 1 fulfill the unusual condition or not? Fulfill. Yes, then we choose this alpha. But if the alpha 1 we get is not here but here, okay, which is still not fulfill the unusual condition, then alpha 1 is not working. Okay, does not work. We will get the alpha 2. Alpha 2 same. Alpha 2 is the alpha 1 multiplied with the same reduction ratio rho. We get alpha 2. Sorry, this one should be the other way. Okay, so we get alpha 2. Okay, if the alpha 2 now fulfill the unusual condition, then we choose alpha 2. Okay, so this is so-called the backtracking line search method. Very simple. Just keep on reducing the alpha. Okay, start from a large value like alpha equal to 1. So if alpha equal to 1 is not working, then we keep on reducing it with the contraction factor rho, which is less than 1, greater than 0. Okay, until you find an alpha which fulfill the unusual condition. So this is what the algorithms work, how the algorithms work. Okay, we start from alpha, okay, which is greater than 0, for example 1. Okay, and then we have a rho, okay, in between 0 and 1. Okay, this is a C, the curvature the constant for the Armature conditions. Okay, we start with this alpha. Okay, we check whether this Armature condition, this is the Armature condition. Okay, is it fulfilled? If it is fulfilled, then we use the alpha. Okay, if not, we multiply the alpha with the contraction factor rho. Okay, we keep on doing this until a sufficient condition is achieved. Okay, I mean the good alpha is achieved. Okay, we found a good alpha, then we stop, then we use the alpha we find there. Okay, let's look at the exercise questions. So for the first question, okay, we have this function. Okay, we want to compute the gradient and also the Hessian of the function. Okay, and then we want to show that at the point x, which is equal to 1 1, x 1 1, x2 also 1. Okay, this is the only local minimizer of the function. Okay, and then the Hessian matrix at that point is positive definite. Okay, this is what we want to do. Okay, let me copy. 1 minute. Copy. Oh. Copy this one to another page. So now, firstly, what we want to do is we find the gradient and Hessian of the function. Okay, so for the gradient, okay, of the function, okay, it's a vector, okay, with two elements. First is the df dx1, okay, then also we have the second one df dx2. Okay, we derive, okay, for s1 and s2. Okay, so to derive for with respect to s1, okay, we derive with respect to s1, we have, okay, 2 and 100, you have 200. Okay, s2 minus s1 square. Okay, and then you derive the internal part, you have negative 2s1. Okay, and this one you have plus 2. Okay, bring out the 2 here, you have 2 1 minus s1, and then the internal you have s1. Okay, so this is the first one, and second one is the, okay, you derive with respect to s2, you have, okay, this is 200 also, and then s2 minus s1 square. Okay, that's all. Okay, because you derive for s2, you have s1, right? So means you do not need to write. And then for this term, there's no s2, means you get 0. Okay, means you do not need to write as well. Okay, this is the one. So you need to simplify it. Okay, you simplify it, you get negative 400 s1, and then s2 minus s1 square plus, oh sorry, minus 2 1 minus s1. Okay, and this is 200 s2 minus s1 square. Okay, so this is a gradient, and for the Hessian, okay, maybe I copy. this is a gradient. Okay, the Hessian, okay, we refer to this one. The Hessian is, okay, you have df, okay, the second derivative s1, and then this one is the second derivative, okay, ds1 ds2, okay, df ds2 ds1, okay, and then this is okay. So this is the Hessian. Okay, you should find the Hessian in this way. Okay, so the first term 2 derivation over the s1. This one, the second term s1 followed by s2, the third s2 followed by s1, and the last 2 towards the s2. Okay, so this will give us you see, this is a term, right? So you derive it over the s2. Okay, what you get is maybe wait, I think I better write here. Okay, so the first derivative is this one, right? Okay, now we derive again for s1. So you see this one we will have negative 400 s1. Okay, we keep the s1, we derive the internal one, we have negative 2 s1, right? This is 0, right? Derive this one we get 0, this one we get negative 2 s1. Okay, minus 400. Okay, this term, still this term, but we keep this one, we derive this one, we have negative 400 s2 minus s1 square. Okay, and then this one we derive, we have, okay, this one we get 2 negative 1. Okay, negative 1. Okay, so this is for the first term. In the second term, we derive towards s1 already, now s2. Okay, this one we derive for s2, we get 0. For this one, we get negative 400 s1 only. Okay, because this is 0, right? Derive this one, we get 0. Okay, we get this okay, s2 only. So this one also same. s2 we derive for s2 already. Now for s1, we have negative 400 s1 as well. Same with this one. Okay, because it should be a symmetric matrix, right? Sure, you know this is the same. And then now to s2 we get 200. Okay, because this one is a this one considered as constant. Okay, when we derive over s2. So this is the Hessian. Okay, now the next thing is show that s asterisk equal to 1 1. Okay, means at this point s1 1 s2 1 is the only local minimizer for this function. Okay, and then the Hessian matrix at the point is positive definite. Okay, now how to know whether it's a local minimizer? Okay, you see from the function from the Hessian we have here, oh sorry, the gradient we have here, let me copy. I copy to there. Let me check correct now. Yes, okay. So you see, when we are at the local minimizer, the gradient should be 0. this one should be 0. Okay, so if this is 0, that means both are 0. Okay, so here 200 x2 minus x1 square is equal to 0. This guy, okay, is equal to this 0. That means you can find this one means x2 equal to x1 square. Okay, when x2 equal to x1 square, this is 0. So if this is the case, this part, oh, this one is also 0, right? This one is also 0 means that negative 400 x1 x2 minus x1 square minus 2 1 minus x1 is equal to 0. But this term you can see s2, if s2 equal to s1 square, okay, this is 0. So the whole thing here is 0. That means 2 1 minus s1 is 0. s1 is equal to 1. So s1 is equal to 1. We come back to here. s2 is also equal to 1 also. That means, okay, the only chance to have a local minimizer, okay, is at s1 1, s2 also 1, because we need to have 0 at the local minimizer. So this is the answer for this one. Okay, this is, we have proved that this is the only local minimizer. But is it a positive definite? Okay, you see s1 is 1, s1 is 1, s2 is also 1. We come back to here, so we substitute this one to 1 here. Okay, this is Hessian. Okay, the Hessian, I copy, wait, let me copy. Copy everything here. Okay, this is the Hessian. Okay, so at the Hessian, okay, the Hessian at the point s1 equal to s2 equal to 1. Okay, you substitute, you find that the gradient of fs, okay, the Hessian of fs is equal to negative 400, negative 2, right? Substitute 1, okay, minus 400, this one is 0, minus 2, or plus 2, okay, and then this is negative 400, this is negative 400, this is 200. This is equal to how many? Negative 400, negative, wait, let me check. I think maybe there's a mistake here. Let me go back and check. The Hessian, should be correct. Okay, just come back. Okay, so okay, so we substitute s1 and s2. So this is equal to 800. 0 plus 2, okay, 802. Okay, and then this negative 400. this is negative 100, this is 200. Okay, so this is a Hessian at probably I should write this instead of writing this one. I should write this. This is at the 1 1. Okay, the Hessian at 1 1. Okay, so is this a positive definite Hessian? So what we do is first we check whether this one is because this is a 2 by 2 matrix, right? So first we check this number, is it positive? Yes, it's positive, right? And then second we check the determinant of this. Okay, 802, negative 100, negative 100, 200. Okay, so we check the determinant of this one. This is equal to 200 minus 400, negative 100, negative 100. This is equal, yeah, okay, this is correct. This is equal to 2. Okay, correct. Correct 2. So since this is positive, this is a positive definite matrix. Okay. Okay, for question 2, we have a as a vector. Okay, A is a vector and B is a symmetric matrix. Okay, A is a vector, B is a matrix. Okay, compute the gradient and Hessian of this function and this function. Okay, you see, seems like we have to do a lot of things. Okay, there's a lot of calculation here, but in fact, okay, when we have F1 as A transpose X, okay, the variable we have, okay, the X, okay, which is a vector, okay, which is a vector also, actually, when you do the derivative, okay, you'll find that actually it's just like a number, okay, just like a single number. So the gradient of f, okay, what I mean is if y equal to ax, okay, not a vector, you get dy dx as a, right? Same here, you have gradient of f1 is just a transpose, okay, just a transpose. Therefore the Hessian of f is 0, okay, because this is just a constant. Then how about this one, the f2? S transpose A S. This one is just like f2 is equal to A S square. Okay, if you consider this as a number, not a matrix and vector, this is just like just in this one. So when you find the gradient, this is just equal to 2ax, okay, 2ax, okay, and then of course the Hessian is just 2a. Okay, for question 3, okay, you see we have a function here. Okay, we want to find the first and second derivative of the function. Okay, and then we have ABC here to solve. A is okay, argue why the point 0 0 marked with the asterisk here. Okay, this one I think 0 0. This one there's an asterisk here. Cannot be local minimizer. Okay, this point is not local minimizer. Okay, first, second, B, show that the Hessian, okay, when S is 0, does not satisfy the property of this one. Okay, and then third, local minimizer of F is this point. Okay, verify that the first order necessary condition for optimally are satisfied at as a string. Okay, so let's start with the first part. We want to find the first and second derivative of this function. Okay, let me copy. Okay, this is a function. So the gradient of the function, or first derivative of the function, is, you see, this is quite straightforward. Okay, we have two variables here, right? S1 and S2. So this is df ds1 df ds2. Okay, so this is the one, and then we have, okay, derivative of s1 is 4s1 cubed plus, okay, s2 only, and then, okay, this is 0. Okay, so for derivative over s2, this is 0, but you have s2 here, and sorry, I mean what I'm talking about, just s1. Okay, that's all. Okay, for the derivative over s2, you have s2 here, so s1 here, sorry. Okay, derive over s2, you have s1, and derive over s2, you have 2. Okay, 1 plus s2. Okay, this is the gradient. This is the gradient. Okay, then the Hessian, okay, and df okay, okay, this one, and then, okay, you derive over s1, you have 3 4 12 s1 square, and then this one derive s1, you have s2, you have 1 only. This one also 1. This one you derive over s2, you have 2. So this is the Hessian. Okay, so you see, now we part A, we want to argue that at point 0 0, okay, this point, okay, cannot be a local minimizer. Okay, for a local minimizer, okay, it is a point where the value of a function is become minimal. Okay, but looking at the contour, looking at this contour, you see this contour suggests that the value of the function is very high here, here. Okay, red color, you see, red color, it decrease, okay, with the line you decrease until here, okay, until this area. Okay, just like the contour of the plot is just like the contour of a map. You see, okay, I mean the real world map. Okay, keep on decreasing until this point. Okay, keep on decreasing until this point. So at this point, you see, it is at a position where the value of function is still decreasing. Okay, means it is not the minimal. Okay, because you can get a lower point here. Okay, higher here, lower here, right? It is still decreasing until it reach here. So this should be the local minimizer, not this point. So this is for part A. For part B, so that the Hessian, okay, this one, when s is 0, y is 0 as well, I mean s1 s2 are 0, okay, does not satisfy the property of this one. What is this? This one means that, okay, a vector, transpose of a vector, product with the Hessian at this point, and with the vector again, okay, is greater than 0, okay, for all the p. Okay, we don't know what is a p, we don't know what is a vector, but when we do this product, we have something greater than 0. Okay, let's look at the Hessian when the s is 0, when the s1 and s2 are 0. So you see, this is the Hessian. Okay, this is the Hessian. When okay, I write here Hessian of 0. Okay, both s1 and s2 are 0. This is equal to what? This is equal to, you substitute 0 here, you have 0, 1, 1, 2, right? This is the Hessian when this is 0. So obviously, this is a 0, and that means this is not a positive definite. This is not positive definite. So since this is not positive definite, this property cannot hold, because this is a property of a positive definite matrix, right? So you have shown that using the concept of positive definite. Okay, third, part C. Part C, a local measure of f is, okay, of f. The local measure of f is this point. Okay, verify that the first order necessary condition of optimality are satisfied at this point. So what is the first order necessary condition? The first necessary condition says that when it is a local measure, if s asterisk is a local measure, okay, the gradient of f s asterisk is 0. Okay, this is the so-called the first order necessary condition. So you bring this point, 6959 s1 6959, and s2 is negative 1.3479. This is s2. Okay, what you do is you substitute this value to here and here. Okay, s1 to here, s2 to here, and also to here and to here. Okay, you will find that. Okay, you will find that this is equal to 0, 0. Okay, if you find this, that means you have proved this.